First of all, I would like to thank the organizer for inviting me to QCrypt2017. And my name is Koji Azuma. This work was done with my nice collaborators, Mr. Akihiro Mitsutani, Professor Hoikonro, and Dr. Kokado. Before starting my talk, I would like to thank them sincerely. Okay, let's start. Today, I would like to talk about quantum internet. What is quantum internet? The concept of the quantum internet has firstly been mentioned by Professor Kimbo of Caltech in the paper published in Nature 2008. I know nowadays everybody simply refers to this paper when we would like to argue some recent results are related with the concept of the quantum internet. This is because the title of this paper itself is a quantum internet. That's why very extremely useful for us and appealing for general audience. However, this paper mainly focuses on the experimental implementation of the quantum repeater at that point. And therefore, this paper is not so theoretically oriented, not so theoretically rigorous. However, even for theorists, still, this paper includes many nice messages. For example, Professor Kimbo has started his paper by stating that quantum networks provide opportunity and challenges across a range of intellectual technical frontiers, including quantum computation and communication and methodology. I completely agree with this notion. In fact, Kimbo has provided a nice abstract viewpoint about the quantum network. Namely, he defines a quantum network should be composed of quantum information processing node and quantum channel to connect such a node. As you can easily imagine that from the abstract nature of the quantum network, actually this concept is general enough to include many kinds of implementation of quantum information processing tasks found in your community. For example, the quantum repeater, distributed quantum computation, quantum simulation, quantum network of clocks, and longer baseline telescopes. Therefore, the concept of the quantum internet may provide a unified viewpoint on the implementation of the quantum information processing in general. Therefore, it is very important to understand the full potential of the quantum internet. Today, I would like to challenge to answer this question partially. My talk starts by asking what is the most primitive function of the quantum internet? It must be two-party communication over the network. Imagine the future where we have a large-scale quantum network described by this type of graph. Okay? As Kimbo has considered that this quantum network is composed of quantum information processing node and quantum channel. Okay? The two-party communication is supposed as follows. Namely, suppose that there are two clients called Alice and Bob who want to share the entanglement of private bits by utilizing such a given quantum network and combining LOCC. In particular, the recipe for two-party communication is described as follows. The goal of the two-party communication over the network is to supply Alice and Bob with entanglement or E-bit to perform quantum teleportation or private bits to perform unconditionally secure communication. This is the goal of the two-party communication over the network. What does a node in the network represent? Each node corresponds to a quantum information processing node, such as quantum repeater nodes or quantum computer. Okay. What does the edge in this graph represent? Each edge corresponds to some quantum channel, such as optical fiber or free space for satellite-based quantum communication, and namely that each edge corresponds to some general quantum channel. Of course, such a quantum channel includes a noise in general. For example, if we connect some node by using optical fiber, in such a case, depending on the length of the optical fiber, which includes a loss. Therefore, in general, such a node in the graph network is represented by quantum noisy channel, namely in CPTP map in general. Okay? In contrast to classical network theory, we have a free resource for the case of the quantum network. Such a resource is regarded as local operation within each node and classical communication among the nodes. Namely, we can freely utilize the so-called LOCC operation. Okay? The main question today, my talk, is how much efficiently we can provide E-bits or private bits to Alice and Bob by utilizing such a given quantum network and LOCC. This is the main question I would like to ask. I would like to answer through this question, this talk. Okay? In particular, I would like to talk about, give a upper bound and lower bound of the optimal performance of these most basic type of quantum internet protocol. This talk would be based on 2 papers recently appeared in Nature Communication and Physical Review A. And in addition to you, please check another paper, nice paper given by Pirandra, which you can. This paper is also given almost at the same time as our paper. Okay, my main contents of this talk is based on 2 contents. First content will give a general upper bound for quantum internet protocol. The second part of my talk will give a universal protocol which works over any kind of quantum network. Okay. Namely, first part will give a low upper bound, and the second part will give a lower bound on the optimal performance of the quantum internet protocol. Okay, let's start by considering a general upper bound for the general quantum internet protocol. Before providing such an upper bound, we need to start defining what is the most general quantum internet protocol by utilizing this type of physical layer of quantum network. Of course, as I said, everybody can freely utilize LOCC operation. Therefore, they should start by preparing some quantum state. Of course, just using the LOCC, therefore, such a state should be a separable state in general. Okay. The next step is we want to use some quantum channel. For example, in this case, suppose that Alice uses some quantum channel between her node and another node called C1 here. Then again, everybody performs the LOCC operation. Such a LOCC operation provides outcome K1 with some probability pk1. Okay. Depending on such outcome of the LOCC, somebody again uses a quantum channel. Okay. After that, everybody again performs the LOCC operation, which provides a new outcome K2 with probability pk2 conditioned by K1. Okay. Namely, that the general protocol is described like use of the quantum channel and the LOCC alternate manner in general. Okay. This type of operation continues until the final round, say else round. For example, in the else round, we finally perform the LOCC operation, which presents a final outcome KL with probability described like this form. Anyway, through this type of most general internet protocol, we should provide a final quantum state, which should be described like this form. Here we call such a state log KL here, which should be given by some probability pkl. Again, our focus here is to the 2-party communication over the quantum network. Therefore, the final state for such a state for Alice and Bob's system should be close to target state, such as maximally entangled state or private state. Namely, such a reduced density operator for Alice and Bob's system should be close to target state, tau dkl here. Tau dkl represents a state from which log 2 dkl E bits or private bits are distillable by utilizing LOCC. Okay. Then we can now define the general internet protocol. The next question, how to derive upper bound. Okay. The main idea of us is extremely simple, extremely simple. We just consider bipartite cut of the quantum network. Okay. In order to consider such a bipartition, we introduce a fictitious party called Big Alice and Big Bob here. Namely, suppose that all the node within the orange region is held by a single fictitious party called Big Alice here. All the other nodes within the blue region is assumed to be held by fictitious party Big Bob here. Then our idea is the following. Namely, we just regard given general quantum internet protocol as point-to-point communication between Big Alice and Big Bob. What is the idea behind this one? Actually, if we have general quantum internet protocol which finally provides E bits or private bits to Alice and Bob, at least in such a case, such a protocol should work as provide the same size of E bits or private bits even to the Big Alice and Big Bob. Therefore, that if we have upper bound to such a point-to-point communication between Big Alice and Big Bob, such upper bound should be also upper bound for the given quantum internet protocol in general. This is the main idea of our talk. As an example of the upper bound, we just borrow the idea, recently derived upper bound called Takeoka-Guha-Wild bound or TGW bound now. Okay. Of course, in the course of the derivation, we need to have a small generalization of the TGW bound. Anyway, our main idea is extremely simple. Namely, we just consider bipartite cut of the quantum network. And we just apply some upper bound to such a simple bipartite quantum communication protocols. Then today I would like to skip the details of the proof, but the main conclusion is very beautiful and simple. Okay, our upper bound is described like this. Okay, for any choice of the bipartition of the network, namely for any choice of the big R's and big Bob, we always have this type of inequality. Left-hand side of this inequality represents a average obtainable E bits or private bits through such a general internet protocol. Okay? On the other hand, right-hand side of this inequality represents how many times of a quantum channel between big R's and big Bob are used, and the Scheduled entanglement of channel for such a channel connecting big R's and big Bob. Namely, left-hand side of this inequality does not depend on the choice of the bipartition. On the other hand, right-hand side depends on the choice of the bipartition. Therefore, finally, we need to minimize the right-hand side of this inequality. However, our inequality holds for arbitrary choice of the big R's and big Bob here. Okay? But the important message here is that we can always estimate the first term of this right-hand side inequality, because we just use the Scheduled entanglement of the channel, which is a single letter formula. Therefore, we can always estimate at least upper bound of such a quantity. This is a striking contrast with quantum capacity of private capacity in general. The second term of this inequality is just a small quantity we can ignore for the analysis usually. Okay. Okay. Actually, instead of giving a proof of this upper bound, let us consider the application of this upper bound. Okay. First application goes to the general linear network. Okay. Suppose that just a simple quantum network described by like a general, just a linear network. Alice and Bob share many repeater nodes, and all the repeater nodes is connected with the adjacent node by some channel described as CPTP map here. In this case, we can reduce this general inequality in this manner. Namely, we just changing the choice of the big Alice and big Bob or bipartition. We can obtain the different type of right-hand side quantity. Okay? But anyway, we can obtain this type of inequality here. The left-hand side of this inequality again represents average obtainable E bits or private bits. On the other hand, right-hand side of this inequality represents average number of times of quantum channel between the adjacent nodes is used, and times Scheduled entanglement of such a corresponding channel. Okay. If we here fix the average total number of channel use, this is just a summation over all the channel uses. In such a case, we can derive this type of simplified inequality. Okay? The left-hand side of this inequality represents average obtainable E bits or private bits per total channel use. Therefore, this left-hand side of this quantity is related to the so-called rate of the communication protocol. On the other hand, right-hand side of this inequality represents proportional to the harmonic mean of the Scheduled entanglement of the channel between Alice and Bob. Okay, this is applicable to any type of general linear network. Let us consider more specific example. First example is to the application to the adaptive MDI QKD protocol. Okay. Actually, such adaptive MDI QKD protocol are known to work this type of physical layer of quantum network. Namely, in this case, Alice and Bob share only single node, single repeater node. And such a single repeater node called Charlie is connected with Alice and Bob through the optical fiber. Of course, optical fiber includes photon loss. Therefore, the transmittance of the optical fiber is described by exponential function of the length of the optical fiber here. Okay. Of course, for example, that BBM92 or Eckert protocol, MDI QKD protocol should work by using this type of physical layer of quantum network, for example. Okay. But importantly, now the present question is that whether our obtained upper bound is good or not. In order to answer such a question, let us derive our upper bound. Again, as I said, once we are given physical layer of the quantum network, we can derive an upper bound on such a communication rate of the given quantum internet protocol. In this case, we can easily derive upper bound of the ultimate performance of the quantum internet protocol here. Let us compare this upper bound with the performance of achievable some protocol. In this case, we would like to use a so-called adaptive MDI QKD protocol, which are known to present a square root improvement over conventional QKD scheme with the help of of middle repeater node C equipped with matter quantum memory with very short coherence time, or just linear optical devices alone. In this case, we just use a second example as an example here. Okay? And in this example, all photonic adaptive MDA QKD is described like this one. Namely, in this protocol, Alice and Bob first prepared BB84 state locally, and such a BB84 state is sent to Charlie by using the given optical fiber here. Then Charlie first performed quantum non-demolition measurement to know whether such a single photon survives or not of the fiber transmission here. So depending on the outcome, Charlie wants to make a pairing of the only surviving photon from Alice and Bob's side, and Charlie finally performed the Bell measurement only on pairs of surviving photons. Okay, let us compare the performance of this adaptive MDA QKD protocol and our general upper bound. The graph is described like this. Okay? The horizontal axis represents the distance between Alice and Bob. Vertical axis represents the average obtainable, average secret key rates per total channel use. Okay? And in the case, our upper bound is described by dashed curve 1 here. Okay? Dashed curve 1. On the other hand, performance of the adaptive MDA QKD is described by curve 2 here. As you can easily notice that there is no scaling gap between our general upper bound and adaptive MDA QKD protocol. This means that there is not much room to improve further existing adaptive MDA QKD protocol in terms of the performance, because all the protocols should follow our upper bound. Okay? Okay, next application to the quantum repeater. In the case of the quantum repeater, we always consider that this type of physical layer of quantum network. Alice and Bob share that many repeater nodes in the between. All the repeater nodes is connected with adjacent repeater node by optical fiber as well. Okay? Again, once we are given physical layer of quantum network, we can easily derive the upper bound of the communication performance. In this case, the upper bound is described like this form. Okay. Again, let us compare our upper bound with the performance of the achievable quantum repeater protocols. In this case, I just use some simplified quantum repeater protocol in the conceptually. And in this repeater protocol, all the repeater nodes has 2 fault-tolerant matter quantum memory. And this protocol starts by entanglement generation process between adjacent repeater nodes. Okay? And such an entanglement generation process, we first prepare the entanglement between single photon and matter quantum memory. Such a single photon is sent to the adjacent repeater node by using a given optical fiber here. On receiving such a single photon, every repeater node first perform quantum non-demolition measurement to know whether the single photon successfully survives or not. Okay? If such a single photon has successfully survived, in such a case, the quantum information of the single photon is just transferred to matter quantum memory. Okay? This type of entanglement generation process repeated until success between the adjacent repeater nodes. Once all the repeater nodes share the entanglement with the adjacent repeater node, everybody just perform entanglement swapping to provide entanglement between Alice and Bob. Okay, let us compare such a performance of the achievable quantum repeater protocol and our upper bound. Okay. Again, horizontal axis represents the distance between Alice and Bob. Vertical axis represents the entanglement distribution rate per total channel use. Dashed curve represents our upper bound. On the other hand, solid curve represents the performance of this simplified quantum repeater protocol. Okay. As you can, okay, n represents how many number of quantum repeater nodes exist between Alice and Bob. Okay. As you can easily find, independent of the number of quantum repeater nodes, actually there is no scaling gap with our general upper bound and the performance of our achievable quantum repeater protocol, which implicitly means that there is not much room, again, to improve further existing quantum repeater protocol in terms of the performance. Okay, and the next example to the application to the so-called DLCG type quantum repeater. Okay. As well known now, the feature of the DLCG type quantum repeater is to use only probabilistic Bell measurement in any stage, including entanglement swapping. In this case, heralding signal of the classical information should be exchanged over communication distances rather than distance between adjacent repeater nodes. However, during such an exchanging time of the heralding signal, matter quantum memory should decay exponentially with time. Therefore, the question here is that how much coherence time is needed to perform the DLCG type quantum repeater as the theory requires. Even in this case, that we can regard this type of protocol as a linear network composed of the dephasing channel and optical fiber. Namely, we can utilize our upper bound again. We can easily derive an ultimate upper bound of the performance of the DLCG type quantum repeater by assuming the dephasing for matter quantum memory and 10% coupling loss for the fiber. Anyway, you can skip to see the graph. The main conclusion is described like this. At least the coherence time, so-called T2, should be larger than 0.1 millisecond to achieve the DLCG type quantum repeater. Otherwise, there is no meaning to utilize a DLCG type quantum repeater. This type of non-trivial conclusion is obtained by using our general upper bound. Therefore, so far, we have concluded that our upper bound seems to work very well, at least for linear networks. The next question is how about more general networks? In order to answer this question, we need to introduce a new protocol which works over any type of quantum network. Okay. And so we go to the second topic of my talk. Okay. And actually, before providing such a protocol, actually, we first need to observe that inequality more precisely. Okay. Right-hand side of this inequality can be rephrased if we introduce a new parameter called L bar E here. L bar E represents how many times of each quantum channel is used in the quantum network, quantum internet protocol. Namely, the right-hand side of this inequality is completely equivalent here. But please notice that this upper bound suggests us that the average number of channel uses seems to be a very important characterization factor. Namely, L bar E, or how many times of each quantum channel is used, is a nice characterization parameter for the general quantum internet protocol. Okay. Therefore, we first fix the average number of each channel used here. Then, finally, I would like to introduce our aggregated quantum repeater protocol here. Okay. The first step of our protocol is to perform an entanglement generation scheme all over the edges. Namely, for given all over the quantum channel, we just perform some entanglement generation scheme, including an entanglement purification here. Suppose that such an entanglement generation and entanglement purification scheme provides a delta cross L times R delta E copies of a Bell pair. Namely, here R delta represents a performance of such a heuristic entanglement generation process here. Okay. In such a case, after performing such an entanglement generation process all over the edges, we should obtain some Bell pair network described like this. Okay. This is a state network rather than channel network. Namely, more precisely, in the graph below, each undirected edge corresponds to one E bit. Okay. How many number of E bits exist depends on the performance entanglement generation process. Okay. But anyway, by just assuming the existence of such an entanglement generation scheme, we can transform from quantum channel network into the state network described by Bell pairs. Then here we should notice that one fact. For example, if we find one AB path, namely if we find a Bell pair that connect Alice and Bob, which is called AB path here, and if we have such a one AB path, such a one AB path should be transformed into the one E bit between Alice and Bob by performing entanglement swapping along this line. Okay. Therefore, this protocol itself is very closer to the quantum repeater usually. And the next step, therefore, that our protocol is to perform entanglement swapping along AB passes to supply Alice and Bob with E bit as many as possible. Therefore, the question here is how many number of AB paths exist for such a given state network. This was answered already in the graph theory. Okay. Menger's theorem states the following. In the Menger's theorem suggests us that in any graph G with two distinguished vertices A and B, which is regarded as Alice and Bob here, the maximum number of pairwise H disjoint AB paths, this is our focus quantity, such a quantity is equal to the minimum number of H's in a AB cut. The concept of the AB cut is very similar to the choice of the fictitious party called Big Alice and Big Bob here. Namely, for example, in this graph, we can choose, for example, the big Alice and the big Bob in this manner. In this case, we can easily show that the minimum number of edges connecting such a big Alice and big Bob is a minimum. Namely, minimum number of edges in such a given bipartition is 3 in this graph cases. Okay, in this case, according to Menger's theorem, we should find 3 distinct AB paths here, right? Indeed, we can easily find such a 3 distinct paths for given such a Bell pair network. Okay? Therefore, Alice and Bob should obtain 3 E-bits for this type of graph cases by performing entanglement swapping along such 3 distinct AB paths. Therefore, in general, the performance of a protocol is written by this type of form. Namely, Alice and Bob, through our aggregated quantum repeater protocol, Alice and Bob should obtain this size of E-bits with error this type of manner. Then here, please notice that the fact that, please remember our upper bound. Here is that you can easily find that our upper bound, general upper bound, is in the same form of the obtainable E-bits through the aggregated quantum repeater protocol here. Therefore, if there is a nice entanglement generation protocol whose performance has no scaling gap with some scarcity entanglement of the channel, in such a case, our aggregated quantum repeater protocol has no scaling gap with our general upper bound, irrespectively of the network topology. In fact, this is the case for Rossi optical channel networks, namely optical networks. Namely, because we have nice entanglement generation process based on just a single photon transmission. In this case, whose performance has no scaling gap of the scarcity entanglement of the channel for Rossi bosonic channels cases. Therefore, we can conclude our aggregated repeater protocol has no scaling gap with our general upper bound, and irrespectively of the network topology, which answers the first question, namely whether our upper bound is good even for general network should be answered to be true here. Therefore, our aggregated quantum repeater protocol has no scaling gap with upper bound for arbitrary optical networks. Finally, I just briefly mentioned about the optimality of our protocol in general. We can take a asymptotic limit of our protocol, namely just by using some technique, we can derive some condition such as described like this form. Namely, we can derive 3 conditions such that our aggregated quantum repeater protocol is indeed optimal. In other words, if these conditions are satisfied, then our aggregated repeater protocol achieves the quantum or private capacity over the network. Actually, if we combine these results with a recently derived nice paper given by Probe, published in recently Nature Communication, if we combine our condition with such a probe bound, in such a case, these conditions are concluded indeed satisfied for erasure channels, dephasing channels, bosonic quantum amplifier channel, and Rossi optical channel. Therefore, our protocol works as an optimal entanglement key distribution over any quantum network composed of these practical channels. In other words, our protocol indeed achieves the quantum of private capacity over the network, at least for 2-party communication. Finally, and this is a summary of my talk. And finally, I would like to briefly mention about a more recently obtained nice result in our field. Recently, there are many nice papers in our field. For instance, please check the following at least. For example, as I said, Stefano Pirandola has provided a nice upper and lower bounds on the various quantum network scenario by using his teleportation stretchability technique. And in addition to our colleague, Stefan Baumer, generalized our upper bound to be applicable to the GHG state distribution over arbitrary quantum network where such a network may include a broadcast channel. In addition, our colleague Rico Bacca also enabled us to use the relative entropies of entanglement rather than scarcity entanglement of the channel as upper bounds of the 2-party communication over arbitrary networks. We also pointed out a nice paper is given by Delft group, and such a short theater provides an efficient quantum network routing method by borrowing the idea of the classical network routing. Anyway, the final message of my talk is now it's time to play with the concept of the quantum internet. Please try to regard all kinds of quantum information processing as a quantum internet. Thank you for your attention.